Welcome to Hartman Math. Today we're going to take a look at partial fractions. Prior to that, a little bit of review on earlier material in Chapter 7. So solve our system by substitution. Pause the video here and resume when you're done. So notice that the second one's already solved for y, so we'll use that. We'll substitute into the first equation. So we replace the y with 2x plus 1. We need to square the binomial, so 2x plus 1 times itself. And then when we combine all the like terms, we're going to get 5x squared plus 4x minus 28. We do want to get it equal to 0 so that we're now able to factor that. And using the zero product property, we get x equals negative 14 over 5, as well as x equals 2. Those are our x's. We need the y's to go with them. So substitute in. I would choose the second one because for the first one, you're going to get multiple answers, but we really only want the y that is 2 times the x plus 1. So 2 times x plus 1. We get negative 23 over 5, and 2 times the 2 plus 1, we get 2 comma 5. Those are our two solutions. Were we to graph, those would be the points of intersection. 7.4, partial fractions. This is definitely a calculus skill, something that you would use in calculus, where we are going to take a fraction that looks like this and pull it apart into a combination of two fractions that have linear denominators. So we're going to learn how to do that. Fair warning, the process that I'm going to go through is a little bit different than the process that the book uses. Both will work. Example number 1, distinct linear factors. And what that's going to mean is our denominator is going to have the distinct linear factors. So step number 1, let's make sure we factor the denominator. And distinct means we have two separate and distinct factors. X minus 5, we have one of those. X plus 2, we have one of those. Those are our distinct factors. So this is the process that's going to apply here. So we're going to split this up into two fractions added together that have denominator of this one and second one, this one, with unknown numerators. So we're going to say a over x minus 5 plus b over x plus 2, unknown numerators. So now what we're going to do is we're going to add these together. So notice this one, so we have to have a common denominator to add them. This one is missing an x plus 2 because this is our LCD. So multiply top and bottom by x plus 2. This one's missing the x minus 5. Multiply top and bottom by x minus 5. And then from this point, we're just going to focus on numerator and say, my numerator here has to be the same as my numerator here, with a coefficient here of 1. And then we're going to set up our system. Our system comes from the different parts here. We have an x term, which is created by a times x plus b times x as we would distribute. So as far as the coefficient of x, the 1 is equal to a plus b. And then the 16 is made up of the constants, which is the a times positive 2 and the b times negative 5. A times positive 2, b times negative 5. That makes up our constant term of 16. So now we have a system of equations which we would solve. I think I would take advantage of the fact that the b's are already opposite signs. So if I multiply the top equation by 5 and add it to the bottom one, we're going to eliminate the b's. 5a plus 5b equals 5. 2a minus 5b equals 16. Add straight down. 7a is equal to 21. That leads us to a equals 3. And if we put that here, 3 plus b equals 1, we're going to see that b is negative 2. And if you had, when you were doing yours, had these two reversed, you would probably find these two reversed, and that's fine. So now we have to take these and put it back here. So we've got 3 over x minus 5 plus negative 2 over x plus 2. And that negative 2 probably best comes out in front as a negative. If you had these reversed where it's negative 2 over x plus 2 plus 3 over x minus 5, that is the same thing. Example number 2, repeated linear factors. Here's our other situation. Again, we're going to step 1 factor the denominator. So it's going to start with a GCF, and then I think we can factor the trinomial from there. And it turns out it's going to be x plus 1, and another x plus 1. We are best off to write that as x plus 1 squared. So we're talking about repeated linear factors. The x plus 1 as a factor is repeated. So when we break this up into fractions, we're going to have a denominator of x, a denominator of x plus 1, and then for the repeated, a denominator of x plus 1 squared. So that's going to mean 3 fractions, so our unknowns a, b, and c are the numerators. So now we're going to go ahead and add these together. Again, here's our LCD. So this one's missing x plus 1. Multiply that top and bottom. This one's missing an x and an x plus 1. Multiply that top and bottom. This one's just missing an x. Multiply that top and bottom. Now, like as you saw in the previous one, we're really just going to focus on numerator at this point. So a times what was missing plus b times what was missing plus c times what was missing is going to equal our numerator here. And now as we kind of simplify this and square the x plus 1 and do x times x plus 1, we would get that. And now we should be ready to create our system. And the system is based on the coefficients here. So something equals 7, something equals 6, something equals 2. So the 7 is all the x squared stuff. So that's a, that gets you x squared, plus b, and this one doesn't have any. So it's just a plus b is equal to 7. And now let's go after our x's. So something equals 6. Where are we going to get x's? A times 2 gets us x's. So 2a. B times x, so plus b. Cx, so a c. So 2a plus b plus c is going to be 6. And then our constant is the one that comes from the constants. That would be a times 1, so a. There's no constants here, and there's no constants there. So it's just a equals 2. Which is obviously very helpful here in our solving. We know a is 2, so if we substitute that here, we're going to get b is 5. And then we'll substitute both of those here, and we got c is going to be negative 3. So a is 2, b is 5, c is negative 3. It goes there, and then there is our final answer for our partial fraction decomposition. That's it for today. See you next time.